So the next section, the next part is limits and continuity. So many things, many techniques and definitions in multivariable calculus are very, very similar to one variable calculus, which we've seen in like more elementary courses. Well, one of them is limits or continuity. So suppose we have a function, say R. We show it with this, like this, a function from R to R2. Rather than a function from R to R. It's a function from R to R2. So I would show the variable in the domain with T. I would show the variable in domain with T. And I would show the variables in target space or in codomain with X and Y. Okay, so a function from R to R2 can be something like this. I should say, what is R of T? This is something in domain. It can be something like this. It can be, say, T squared plus 1 and say sine of T. You see, our functions they have two components, first component and second component. And I would show the first component with X and second component with Y. So what it means here is that first component X here itself is a function of T, it's T squared plus 1. The second component Y itself is also a function of T, it's sine of T. Okay, we can have functions from R to R3, functions to R3, three-dimensional space. Well, the domain, so the question is why here we have just one R, is that the question? Do I understand the question correctly? Can you explain that more? Yeah, so we can take anything as domain and as target. So we can have functions, say R, from Rn to Rm, say R13 to R, I don't know, 53, whatever. So I'm looking at the most basic examples of functions. We've seen them before are the functions from R to R, right? The functions we've seen in Calc 1 or in high school, for example, y equals x squared. Here, the variable in domain is x, the variable in codomain is y. The second kind of, if we want to go one step further, we look at two functions from R to R squared. We can look at, for example, two functions from R squared to R squared, or we can look at the functions from R squared to R. All of them are possible. But now we are looking at this example. These are the functions from R to R squared. So we can look at the functions from R to R cubed to R3. R to R3. So for example, we can define a function with anything we want. It should have three components. So if it's in R3, there should be three components. For example, say 3 times t is the first one, ln of absolute value of t is the second one, and I don't know, cosine of t is the third one. Here in R3, we show these variables with x, y, and z. So here, x itself is a function of t, it's 3t. Y is a function of t, it's ln of absolute value of t. And z itself is a function of t, it's cosine of t. Okay, they're just functions. There's nothing special about them up to this point. It's just a definition. We can just have functions from R to R2 or R2 to r to r3, for example. Okay, so we can take limit, derivative, and integral of these functions. Well, there's a question. Are we going to learn more matrix algebra with n variables in this course? The short answer is yes. So here we have a function RT, say, whatever, say, I would show the first one, let's say it's sine of t over t. The second one is t squared. And the third one is, well, let's say cosine of t. Okay, so this is a function here. R is a function from R to R3. Now we can take limit of these functions. For example, what is limit of this function R of t when t goes to 0? When I say limit, well, this is a limit of, well, yeah, but let's first define what does the limit means. We have three functions here. We have sine of t over t, we have t squared, we have cosine of t. What do we mean by limit? It basically means take limit of all of them. So when we take a limit of these functions, it simply means we should take limit of each of them, right? So what is the limit of sine of t over t? How can I compute the limit of sine of t over t? Well, so now I should compute the limit of these three functions. So first I should compute the limit of sine of t over t when t goes to 0. Well, when t goes to 0, sine of t also goes to 0. So what I have here, it goes to 0. What I have here, it also goes to 0. This is actually the case for, as mentioned in the comments, it's the case for L'Hopital. And I think we really write L'Hopital like low hospital. I seriously think it should be written as, am I right? L'Hopital rules. Yeah, it's like hospital. Okay, so what does it say? It says when we have a fraction, no, there is a S. Yeah, it's actually, it comes from, well, I'm not sure about the correct pronunciation, but it's the French mathematician Julien de L'Hopital. Well, maybe there isn't. I'm not sure. I'm not 100% sure. I would search. Probably there isn't. Probably you're right. Okay, anyway. With S or without S. Yeah, probably there isn't. Okay, so we have a correct answer here between our arguments about S. Okay. Oh, both are correct. Oh, thank you. Okay, that might be correct. Maybe both of them are correct. I'm not 100% sure though. So probably both of them are correct. But anyway, it says when we have a fraction and when we are taking a limit and when both of them are going to 0, we are allowed to take their derivative. Derivative of cosine, sine is cosine. Derivative with respect to t. Derivative of t is just 1. So we are taking derivative with respect to t. And then take limit of that. Well, that's just cosine of t. And when t goes to 0, it's just cosine of 0, which is 1. So the first limit is 1. When t goes to 0, t squared also goes to 0. And when t goes to 0, cosine of t is cosine of 0, which is 1. So the limit of r of t when t goes to 0 is simply 1, 0, 1. So there is nothing special about these limits. It means we should just take limit of each component separately, right? There is nothing special about that. We would take the limits the way we used to take the limits. Okay. Now there's just one notation I should introduce. What's a limit? What's a derivative? That's a good question. How many people here don't know? Well, raise your hand if you want me to explain limit or derivative. Okay, 2. Okay, you know what it is, but you don't know how to compute it. Okay, okay, one thing I can do is I can continue and then I can come back to limit and derivative, okay? Okay then. Well, let me explain this notation and then we will think about what we can do. So we can write our functions r of t as, say, t squared plus 1 and say cosine of t as a function from r to r2. Or there is another way of writing it. Some people write it as, there's another way of writing the same thing, just a different notation. Some people write it as t squared plus 1 times I plus cosine of t times j. Remember, I and j are the unit vectors. So this is another way of writing the same thing. Or if I have a function from r to r3, say r is t squared sine of t cosine of t, I can write it as t squared I plus sine of t j plus cosine of t, say k. Okay, we use I, j, k. Here I is in 3-dimensional space is 1, 0, 0. J is 1, 0, 1. K is 0, 0, 1. This is another notation we use. Okay. Let me tell you about the derivative of these functions too, and then we would go back and we would discuss these things a little more carefully. So if I have a function, say r of t, yeah, sure. Is there a question here or the previous page? Okay, is that good or there's a question? Okay, let's continue. So suppose r of t is a function, say sine of t and t squared plus 2t. So derivative of r of t, by derivative of that, we simply mean derivative of each of these functions. So we mean derivative of sine of t and derivative of t squared plus 2t. So derivative of sine of t is cosine of t, and derivative of t squared plus 2t is 2t plus 2. Similarly, if I have a function from r to r3, which has 3 variables, let's say it's ln of t, say e to the t, and say tangent of t. What is derivative of this function? I should take derivative of ln. What is derivative of ln? 1 over t. What is derivative of e to the t? Yes, it's itself. What is derivative of tangent? Yes, it's secant t squared. So we take kind of derivative and limit component-wise. So we say derivative and limit. These things are component-wise, which means we take the derivative of limit of each function separately. Well, integral is also similar. So for example, if I have a function r of t from r to r2 equals t squared and say sine of t, if I want to know what is integral of rt dt, I should take integral of each of these functions. Okay, what is integral of t squared dt? Let's just make sure you know what it is. Plus a constant, huh? Let's show the constant with C1. T cubed over 3 plus a constant. What is integral of sine? It's minus cosine. Actually, integral of sine is minus cosine, not cosine. Be careful. So that would be the integral. We can do the same thing for functions to R3. Say we have this function, 1 over t e to the t, and well, just sine of t. So the integral of rt dt would be the integral of 1 over t dt, integral of e to the t dt, and integral of sine of t dt. So let me answer the questions. So the answer is yes. This function is kind of vector of functions. That's why we call them vector valued functions. It means it's a function actually, but it's a vector of functions. And is there a question from the previous page? We are taking integral of a function. We should take integral of each component. Okay. Yeah, you're welcome. So what is integral of 1 over t? Yeah, almost. It's ln, but not ln of t. Can anyone? Well, there is plus a constant, but there is still a small problem there. It's not ln of t. It's ln of absolute value of t. Yes. What is integral of e to the t? Yeah, that's correct. The integral of e to the t is itself, yeah, plus a constant, and integral of sine would be minus cosine, plus another constant. So these constants, they can be different constants. That's why I show them with C1, C2, and C3. Okay, and that would be the things we need to know for the exam. To be honest, I thought maybe some of you have forgotten integral, or I thought some of you might be in high school and you might not know what integral is. So integral wouldn't be in the midterm. So it's not going to be in the midterm. So you would have a time to review it for final or learn it for final. So not in midterm. That's one thing. We are going to have limit and derivative in the midterm, but not integral. The reason is that I thought maybe some of you have forgotten, or you don't know what is limit, derivative, and integral. The point is that these two things are easy to learn if you don't know that, or if you've forgotten. So you would have enough time to review these things for midterm. And you should learn this one for final, because there are a lot of things I'm going to talk about in future. They're going to be related to integral, but not in midterm. Okay, but these two topics are in midterm. The second thing is that we are going to finish this chapter on Thursday. We are going to finish chapter 2 on Thursday. As you notice, chapter 2 is not as challenging as chapter 1. It's not as fundamental, but because it's very close to the midterm, things I'm going to tell you on Thursday, they are not also going to be in the exam, not in midterm. Because they're pretty close to the exam, I thought maybe it's better not to consider these things for the exam. So what is going to be on the exam is what I taught you up to this point without integral. Everything I told you about without integral up to this point would be in the midterm. I would give you one practice exam on Thursday. Okay, so you would have one practice exam. Okay, is there any question from everything we saw up to this point which you're supposed to know for the midterm? I wouldn't send you the answers for the practice test. No, I wouldn't do that. That's not the correct thing to do for the practice test. But if you solve it and if you have questions, you can ask me on Monday or on Tuesday. On Monday from 10 to I think 11, it's my office hours. It's my office hour, and then I would be in MLC. Again, you can find me online from 11 to 1. 2 hours I will be there. You can ask me any questions you have. And yeah, so you don't have credit for homework 1. So now we are going to talk about different coordinate systems. In two-dimensional case and three-dimensional case. Okay, so when we are in two-dimensional space, in plane, we have X and Y. So if we have a point P, we can project it to the X-axis. We get, say, X1. We project it to Y-axis. We get Y1. Therefore, we can show P with X1 and Y1. And we call this thing, this way of presenting the points, rectangular coordinate system. Well, there is another way of doing that, which is very common. The other way is to connect this point P to the origin. We get a segment. We can compute its length. Let's say the length is R. And then we can see what is the angle it makes with the positive direction of X-axis. And let's call that theta. And we can show this point with this pair, R and theta. So this is called polar coordinates. So for example, in polar coordinate system, if they tell us show these lines, for example, if in with the use of polar coordinates, we are asked to find this point 1 and pi over 4 on the plane, well, it simply means look at this angle from the positive direction of X-axis, look at the angle pi over 4, and then in that direction, consider the segment with length 1. At the end of that segment, that vector, you have your point. If it's P, this point is P. Okay? So the important thing here is how we go from polar coordinates to rectangular coordinates. So the idea is that if we are looking at a point P with coordinates x1 and y1. If I look at x1 here, if this angle here is theta and this length is r, this side here is actually r cosine of theta. And this other side here is r sine of theta. Why? Well, because what is the definition of cosine? If we look at this red triangle, cosine is, what is cosine? Cosine is x1. Cosine is going to be this side to r. Therefore, x1 is r cosine of theta. What about sine? What is sine? What is sine of theta? Well, in this triangle, again, sine is this side, but this side is, again, equal to this side, which is y1 over r. So y1 is r sine of theta. This is the way to go from polar coordinates to rectangular coordinates, or vice versa, coming back from polar coordinates to rectangular coordinates. Now, we have the same thing in dimension 3. In dimension 3, there are actually two ways of doing this. One is called cylindrical coordinates. And the other one is called spherical coordinates. Okay, so in three-dimensional space, usually when we have a point P, we look at it, we show it with three numbers, x1, y1, z1. These are some numbers. X1 is something here, y1 is something here, z1 is something here. Well, maybe y1 shouldn't be there, actually. Okay, but there is another way of showing, representing these numbers, which is called the polar coordinates. That's useful. Well, we will see some of the applications of the polar coordinates. What does it mean? It simply means, first, we should look at the, well, here we have x1, y1, z1, and I want to use the cylindrical coordinates. What I should do is very similar to the previous thing. I can look at the distance between the origin to this point. So look at this distance, right? Connect it to that point. Now, if I project, I'm not sure if my drawing is really, maybe it's a little confusing. Maybe I draw it. It's better to draw it more carefully. So this is y-axis, this is x-axis, this is z-axis, x, y, z. And suppose I have a point with some coordinates, x1, y1, z1. So if I construct this cube, the point P would be here. If this is x1, this is y1, this is z1. Okay. Now I want to describe P different using another coordinate system. Look at the image of P on xy plane. So look at this point. This is kind of the shadow of P on xy plane. So if we had sun here, we could see the shadow of P on the ground, and that would be the shadow of P, right? Let's show it with P prime. Okay, that would be this. So P prime would be the shadow of P on the ground. But we also know what is the coordinates of P prime. Note that the first coordinate of P prime is again x naught. Its second coordinate, it's again y naught. The only difference is that its height, the third coordinate, is 0, right? The shadow of P on the ground. Now look at the segment which connects the origin to P prime. This segment. And let's compute its length. Say its length is r. Okay, so suppose length of that segment, which is the distance between P prime and origin, is r. But on the other hand, we know what is the distance between P prime and origin. It's simply x1 squared plus y1 squared plus 0 squared, which I don't need to write. Okay. Also, look at this angle this segment makes with the x direction. Say that's theta. Again, if I look at xy plane, x1 would be r cosine of theta, and y would be r sine of theta. Okay. Now, what I mean by cylindrical coordinates is showing P, describing P with 3 numbers. What are those 3 numbers? Well, r, theta, and z. And these 3 numbers, they're enough to locate P. So let's look at one example. Let's see if we understand what's going on here. So here we can describe or locate points in R3 with x, y, z. This is called rectangular coordinate system. We can locate them with r theta z. This is called cylindrical coordinate system. How they're related? Well, x is equal to r cosine of theta, y equals to r sine of theta, and z, well, it's equal to z. There's nothing about that. Okay.
How about spherical?
Yeah, I would get to that. Let's first look at this example, and I would get to that one too. So for example, suppose we want to locate this point. So find this point, r theta z equals to 4, 5, well, let's say pi over 6 and 3. It's a point in R3. We want to find this point. What does it say? How can I find this point? First, we should look at r and theta. R and theta is something in this xy plane. Okay, so the angle theta is pi over 6. It means from this direction of positive direction of x, it makes the angle pi over 6. So we should look at the angle pi over 6 from this positive direction. And then the length is 4. We should go forward by 4. We get to this point. This is P prime. So this is kind of the shadow of our point on the ground. The point itself is above P prime. How much above? Well, by 3. We should go up exactly by 1, 2, 3. We get to a point. This is going to be P. That's how we find points using these coordinates. Okay. Now, I can find, well, now what I can do is that if a point is given in this coordinate, I can ask you to write down the coordinates of the same point in rectangular system. So question can be something like this. We have a point P, which in cylindrical coordinates is given with r theta z equals to 4 pi over 6 and 3. Write down the coordinates of P in rectangular coordinate system. Well, the equations we need to use are the equations I just mentioned. X is r cosine of theta, Y is r sine of theta, Z is just Z. Okay? So X is r cosine of theta. Well, here r is 4 cosine of pi over 6. So it would be r, which is 4 times cosine of pi over 6. Cosine of pi over 6 is the square root of 3 over 2. We would get 2 square root of 3. What about y? Y would be 4 sine of pi over 6. But sine of pi over 6 is 1 over 2. So we get 4 over 2, which is 2. And what is z? Well, z is z. Z is just 3. So in the standard coordinates or in rectangular coordinates, the coordinates of this point is going to be 2 square root of 3, 2, and 3. So we can write down these cylindrical coordinates in terms of, well, the usual rectangular coordinates. We can convert that to the rectangular coordinates. But we can also go back. What do I mean by that? Well, what I wrote there was how to go from cylindrical coordinates to rectangular coordinates. So in order to do that, these are the equations we used. But what about the other direction? How can we go from rectangular coordinates to cylindrical coordinates? How we can go back? Well, look at x and y. What is x squared? Well, what does rectangular coordinates mean? It means we have x, y, and z. We want to find r, theta, and z. Well, z is given already, so there is no problem about z. We need to find r and theta. But it's just like the previous case. See, here r squared would be x squared plus y squared. And theta would be tangent of y over x. These are the equations we would use for the other direction. So let's look at an example. Suppose a point is given in rectangular coordinates. Suppose I have a point P, 2, 3, 5. I want to find the coordinates of P in cylindrical coordinate system. Suppose this is given in rectangular coordinate system. This is x, y, z. So x is 2, y is 3, z is 5. I want to see what is r, what is theta, what is z. Well, z is 5. What is r? I said we should use this equation. R squared equals to x squared plus y squared. So r is the square root of 13. We take the positive one because I would like to think about it as the distance of a point to the origin. And what is theta? Theta is the angle which its tangent is y over x, 3 over 2. So theta is arc tangent of that. So in cylindrical coordinates, r, theta, and z is equal to square root of 13, arc tangent of 3 over 2, and z is 5. Okay? Is there any question here about how we go from one coordinate system to the other and how we come back? Is it clear for everyone? So what is the purpose? The purpose is that these equations, sometimes, if you look at the equation of, for example, a surface or whatever, sometimes in one coordinate system, they are a lot easier than the other one. Oh, do you have my voice now? Can you hear me or you can't?
Yeah, we can.
Okay. Okay, so sometimes in some coordinate system, the equation is a lot easier than the other one. What do I mean by that? Let's look at an example. Remember, what is the equation of, say, a cylinder here? But, well, the equation is something like this: x squared plus y squared equals 1, right? This equation is actually an equation in rectangular coordinate system. What would be the same equation? What would be the equation of the same cylinder in cylindrical coordinate system? Yep, that's correct. So remember, how should we go from rectangular to cylindrical? We should use this equation. R squared equals x squared plus y squared, and theta is tangent of y over x. We should use these two things. Well, r squared should be equal to x squared plus y squared. But what is x squared plus y squared? We already know what is that. That's just 1, right? Well, r for each point x, y, and z. Okay, so the question is that if I can sketch or show r here. So for each point x, y, z, r is the distance between that point and the origin. So for each point, so for example, what is r for this point? For this point, r would be the distance between origin and that point. So for each point, r would be the distance from that point and of the origin. Okay, yeah, what about theta? There was a theta too. Theta should be arc tangent of y over x. What about that? What is arc tangent of y over x here? What can I say about arc tangent of y over x? Do I need to write that? What is that thing? Does anyone know the answer? Look at, well, I mean, there is a philosophical answer. So when I go around this circle, for example, what is theta here? Theta is this angle, right? If I go around this circle, theta is going to change from 0 to 2 pi. Is that correct? When I go around that circle, theta is going to change. It starts from 0, it would get to 2 pi, right? So theta can be anything, basically. Theta basically can be anything, anywhere you look, anywhere on this cylinder you look. You can go around, and theta can be anything on that circle, anything from 0 to 2 pi. Well, if it can be anything, it means there is no restriction anymore, right? It can be anything, so there is no restriction. If there is no restriction, there is no equation. There is no need to write that anymore. So there is no need to write theta anymore. Kind of like, yeah. And theta, well, not the fact that we don't need to write down anything about theta is very similar here, that we don't need to write anything about z here. So here z is the missing variable. Here theta is the missing variable. So they reflect each other in some sense. On the left side, z is missing. On the right side, theta is missing. Okay, so that's equation of this cylinder in cylindrical equation. Well, which one is simpler? Is this one simpler? Which one is simpler equation? Is the equation of cylinder simpler in rectangular coordinates or in cylindrical coordinates? Well, the answer is cylindrical. That is correct. Why? Because here, the equation, we have one equation, two variables. Here we have one equation, one variable. And if you do math or physics or, well, engineering, pretty soon you would know how much it really matters. When you have one equation and one variable, the life is really easier than having one equation and two variables when you want to solve, describe something. Anyway, the less amount of variables we have, it's more kind of explicit and easier to handle in some sense. Okay, let's look at some other examples. Let's look at other surfaces and try to write down equation of some of them. Let's see if we can do that. So we had sphere. Suppose the sphere with radius 1 around the origin. The equation was x squared plus y squared plus z squared equals 1. This equation was an equation in rectangular coordinates. Now the question is that what would be the equation of sphere in cylindrical coordinates? Well, again, in cylindrical coordinates, we should write down an equation for I, theta, and z. Well, r squared, maybe it's good to write it on the right side. So r squared is x squared plus y squared, right? On the other hand, x squared plus y squared plus z squared is 1. So if I add r squared to z squared, it would be x squared plus y squared plus z squared. So this thing is equal to 1. Again, is there any restriction on theta? Well, look at these circles again. When we go around each of these circles, theta changes from 1 to 2 pi. So in some sense, theta at each level, theta can be anything. So in some sense, there is no restriction on theta. So theta is also missing here. So this is the equation of the sphere in cylindrical coordinates. R squared plus z squared equals 1. Which one is simpler again? The equation in rectangular coordinates or the equation in cylindrical coordinates? Well, the equation in cylindrical coordinates, yes, because here we have one equation, 3 variables. Here we have one equation, 2 variables. Less variables, so it's better. Any question here? If not, let's look at another case. Well, let's
look at... I have a quick question.
Yeah.
So I understand how, like, let's say if you're going from rectangular to cylindrical, like I understand how you get r and theta and z, but I don't get how you got the equation for each of them.
Well, I mean, do you agree
you would have to be given like the equation, correct?
Well, one of the equations is given. For example, here the left side is given.
Right. Yeah.
I want to write down the right side, okay? So I want to write down something, some equations, which only has r, theta, and z in it. Okay?
Mm-hmm.
So here r squared is x squared plus y squared. Do you agree?
Mm-hmm.
So on the other hand, we know x squared plus y squared plus z squared.
No, like I guess my question is, unless you're given, like, for example, the other problem was like x equals something, y equals something, z equals something, find r, theta, and z. Like, if you're given the points, you answer in points. If you're given the equation, you answer in the equation.
Yes, that is true.
Okay.
Yeah, that's correct. Okay, so let's continue. Let's look at more examples. It might clarify more. Suppose we have hyperboloid. Of one sheet. So if you remember, it's something which looks like this. And the equation was, for this one, this is in direction of z, it's extended in direction of z. The equation was x squared plus y squared minus z squared equals 1. Okay, this equation actually is written in rectangular coordinates. Now I want to write this thing in cylindrical coordinates. What would be the equation in cylindrical coordinates? Well, it means I want to write it in terms of r, theta, and z, right? That's what I'm looking for. I want to write down the same equation in terms of r, theta, and z. Well, here x squared plus y squared equals r squared. So r squared equals x squared plus y squared, right? What does that tell me? That tells me here, instead of x squared plus y squared, I can just write down r squared. Then I have minus z squared equals 1. That would be my equation. So the equation in rectangular coordinates is the one I have on left. The equation on cylindrical coordinates is what I have on right, which again is easier to understand. It has two variables. Well, we can look at one more example. Let's look at another cylindrical surface. Suppose we have this surface, x equals y squared. It's written in rectangular coordinates. It's this surface. X equals y squared. X and y are these two directions. X equals y squared is something like this. And then the cylinder above it is going to be something like that. It's a cylindrical surface, and the coordinates x equals y squared is written in rectangular coordinates. Now the question is, write down the equation of this surface in cylindrical coordinates. Well, let's see. Here we know x is equal to y squared. On the other hand, we know x is r cosine of theta and y is r sine of theta. So instead of x, I can write r cosine of theta, and instead of y, I can write r sine of theta. So r cosine of theta is equal to r sine of theta squared. So r cosine of theta is equal to, well, r squared times sine of theta squared. Well, it means I can take both of them to one side. It means r squared r squared sine of theta squared minus r cosine is 0. I can factor r. It would be r times r sine squared minus cosine is 0. Well, I mean, there is just one point where r is 0 there, and that's the origin. So at all the other points, r is non-zero. So I would assume r is non-zero, and I can divide by r. So r times sine squared of theta is minus cosine of theta is 0. If I divide both sides by r, I would get this equation. Therefore, r sine squared is equal to cosine. Therefore, r is equal to cosine of theta over sine squared of theta. which is the same as cosine of theta over sine of theta times 1 over sine of theta. Cosine of theta over sine of theta is cosecant of theta, and 1 over sine of theta is cotangent of theta. And that's what we got. That's our equation. R equals cosecant of theta times cotangent of theta. That would be the equation of this surface in yeah, that would be integral of something. That would be the equation of the surface in cylindrical coordinates. Well, I think the equation, the rectangular equation in this case is simpler, right? I mean, on the other side, you have cosecant and cotangent, and is more complicated. The rectangular coordinates here are easier to handle. But let's go back. Let's do another example in the other direction. Is there any question here? Can anyone, are you, well, if there's any question here, ask. Make sure you can follow the algebra. So here the equation was x equals y squared, and we want to write down this equation in cylindrical coordinates. What I would do, I would say in cylindrical coordinates, x is r cosine of theta and y is r sine of theta. So I would just substitute them into this equation, x equals y squared. I would say x is r cosine of theta equals to y squared, but y itself is r sine of theta. Therefore, r cosine of theta would be equal to r squared sine squared. Right? Now, r squared sine squared minus r cosine of theta would be 0. So r, I can factor this r times r squared, r sine squared minus cosine would be 0. Well, there is exactly one point where r is 0. R is 0, it means the distance from the origin is 0. It means you're at origin. Yeah, there is just one point there, but at every other point, r is non-zero. When r is non-zero, it means I can divide this equation by r, right? If I divide both sides by r, what I would get is r sine squared theta minus cosine of theta is 0. So r sine squared would be equal to cosine. So r would be equal to cosine over sine. Sine squared, sorry. And therefore, I can write it as, I can write sine squared as sine times sine. So I would get cosine over sine times 1 over sine. Now, cosine over sine by definition is cosecant. And 1, oh, it's 1 over sine. It's not cotangent. So, okay, it's good that we reviewed. There's a mistake here, right? Oh, yeah, it's correct. Sorry, I flipped them. So cosine, sorry, I'm following the things from two different screens. That kind of confused me. Cosine over sine would be cotangent here. And 1 over sine would be cosecant here. So r would be equal to cosecant theta times cotangent theta. Okay, so yes, that's the correct question you've asked. How can we go in the other direction? So suppose we have a surface. Suppose we have a surface. Suppose equation of a surface is given in cylindrical coordinates. Oh yeah, that's what I haven't thought about the spherical yet. We have cylindrical and rectangular. I would talk about cylindrical too. So suppose an equation of a surface is given in cylindrical coordinates. Suppose it's this. Well, so it should be something in terms of r, theta, and z. So this is an equation in cylindrical coordinate system. The question is find or write down the equation in rectangular coordinate system. So the equation now is in terms of r, theta, and z. We want to write down the equation in terms of x, y, and z. Okay, that's the idea. We want to write down the equation in terms of x, y, and z. So what are the things we need to use? What are the things we should use? We need to use some facts. We need to know what is x, y, and z. Well, z is z. There's nothing wrong with that. X is r cosine of theta. R is r sine of theta. That's one set of equations. The other set of equations we had was r squared was x squared plus y squared. And theta is tangent inverse or arctangent of y over x. I wouldn't tell you which one you should use. You should yourself think about it. Think about it for a few minutes. Cosine squared. Okay, there's an answer already. Okay, think about it for 5 minutes. See which one of these things you should use and then find the equation in rectangular coordinates. Oh, also, if you don't remember, you should probably you would need also these things for example. So what is cosine of 2 theta? Does anyone remember the formula? Yeah, that's correct. So let me write these two. So sine 2 theta is 2 sine theta cosine theta. And cosine 2 theta, well, one formula is cosine squared theta minus sine squared theta. You need to use these equations here. Okay, so let's see. The equation I'm going to use is the ones on the left side. I'm going to use these equations. The ones in the yellow box. So I can erase the ones on the right box there. Okay. So r squared times cosine of 2 theta. I would first plug in the value for cosine of 2 theta. Cosine of 2 theta is cosine squared of theta minus sine squared of theta. Plus z squared plus 1 is equal to 0. So r squared, let's multiply that. Cosine squared minus r squared sine squared plus z squared plus 1 equals 0. R squared cosine squared is r cosine, the whole thing squared, minus r squared sine squared is r times sine squared, plus z squared plus 1 equals 0. But what is r times cosine? Well, let's look here. R is x. R times cosine is x. So it's just x squared minus. What is r times sine? Well, look here. It's just y. It's just y squared plus z squared plus 1 equals 0. Well, I can continue here. It means minus x squared plus y squared minus z squared equals 1. If I take 1 to the other side and multiply it by negative. Does anyone remember what is it? What is the surface this thing represent? This equation, minus x squared plus y squared minus z squared equals 1. 2 negatives, 1 positive. Yeah, 2 sheet hyperbola in direction of y. So if it's x, y, z, it's looks like this. Something like this. So this was the equation of this surface in cylindrical coordinates, and we translated this equation to rectangular coordinates. That is correct. Any question here? Okay. Okay, so I want to go to spherical coordinates. I think we can continue. Do you feel tired? Do you think you need 5-minute break, or you think we can continue?